Question 9. The compound 1,2-dichloro tetrafluoroethane is a chlorofluorocarbon, CFC, that was previously used as in a refrigerator as a coolant to cool refrigerators, also used in aerosols and the like, anything that can be propelled out of a can. Very dangerous because they contain chlorine, so now been replaced by compounds that can be used in aerosols and refrigerants, etc., that haven't got chlorine atoms in there, and we'll discuss why in a minute. Molecules of 1,2-dichlorotetrafluoroethane can break down in the upper atmosphere to form chlorine radicals. It's where there's ultraviolet light in the upper atmosphere. Give an equation to show the breakdown of one molecule of 1,2-dichlorotetrafluoroethane to form one chlorine radical and one other species. So what actually happens is that one of the bonds breaks, either this CCl bond here or this CCl bond here, but it's the C to Cl bond that breaks in the presence of ultraviolet light. And what actually happens is the pair of electrons, the shared pair of electrons in the bond, one electron goes back to the carbon and one electron goes back to the chlorine. And to show the electrons have gone one way and the other way as well, we put a dot on each of these two atoms to show that once upon a time those two dots, which actually represent unbonded electrons, have actually been part of a covalent bond that's now broken in the presence of ultraviolet light. So what you've got is, you've got CF2Cl, CF2Cl, so I've drawn it as a condensed formula here, goes to, I've broken off this Cl here, but I could have broken off the Cl at the other end. So I've broken this, and this carbon here now has got a dot, and the Cl has got a dot as well. So this bond here is broken, and one of the electrons has gone back onto the C, an unbonded electron here on this C, and an unbonded electron here on this Cl. I could have broken this, so I could have had CF2Cl, CF2 with a carbon, with a dot on the carbon on this carbon here, and a Cl, but I just chose to break this left-hand bond. Give two equations to show a chlorine radical. So these are very, very reactive, these chlorine radicals now, catalyze the decomposition of ozone. So ozone is O3, so it's a form of oxygen, an allotrope of oxygen, a different sort of way of bonding the oxygen atoms together. Still an element, still O, but got three oxygens bonded together rather than a normal allotrope, which is O2. So it forms O3 can only form O2. There's only two different forms of the element oxygen, O3 ozone and O2 oxygen. Two different allotropes of oxygen. So it forms O2, and then you just got to basically work out what's left over. There's one O that's left over, there's a Cl left over, and there's a dot. The dot is actually on the oxygen, so that's where the unbonded electron goes. Then this is going to react again. Any radicals react again. They're very, very reactive. So OCl reacts with even more ozone. That's why it produces a hole in the ozone layer, because it carries on reacting. O3, the only thing that it can make is O2. A little trick here is that you've got four O's on the left, so if you balance it by putting two O2s, that balances up the oxygen, and then the only thing that's remaining is a Cl dot. Look here, the Cl dot is reformed. It's a catalyst, and no wonder then that by making a small number of chlorine radicals in the upper atmospheres, carries on reacting. This is called a chain reaction, where the Cl dot carries on reacting again with more and more and more ozone, and produces a huge hole in the ozone layer, turns lots of ozone into O2, just from a small amount of chlorine radicals from the use of CFCs. 9.3. Butane can be used as a replacement for CFCs in refrigerators. Good, because it's got no chlorine in it. Good, that won't produce any harmful chlorine radicals. Calculate the volume. So what have I got? I've got a volume of butane gas in 101 kilopascals. I've got a gas constant here. So as soon as I see gas constant R, I'm looking towards PV equals nRT. So let's put PV equals nRT out there. What have I got? So let's start with the butane. So I've got an R is a gas constant. I've got a volume in centimetre cubed. I've got a temperature in Kelvin, and I've got pressure in kilopascals. So it clearly wants me to use PV equals nRT on this first part here. So let's just do that bit and then worry about the rest of the question in a minute. PV equals nRT, pressure. Now pressure's got to be in pascals. This is in kilopascals. So pressure's in pascals. To turn kilopascals down into a lower unit value, a smaller unit value of pascals, and multiply by 1,000. So 101 kilopascals is 101,000 pascals. That's in the correct units now. N is number of moles. Here, can I do anything with that? Yes, I've got a mass here. So I've got a mass and I've got butane. I can work out the MR of butane, 4 carbons and 10 hydrogens. I can work out the MR is 58. So I can work out the number of moles. I can work out N of butane from a mass, and MR is 0.669. Good. Temperature is in Kelvin. Should be in Kelvin. Yes, it's already in Kelvin, so 272. If it was in degrees C, I'd have to add on 273 to convert degrees C into Kelvin, but I don't need to. It's already in Kelvin. Good. So I can just put these numbers in now. 101,000 multiplied by the volume that I don't know. That seems to be the missing value that I don't know. N is number of moles. I'll work that as 0.669. 8.31 is the gas constant. R, I've been given that. Temperature is 272 Kelvin, and I can work all of that out. It's 1512.15. So 101,000 pascals multiplied by volume is 1512.15. Divide the 1512.15 by the pressure in pascals, 0.015. It comes out in meters cubed, so volume is in meters cubed. To convert meters cubed down into decimeter cubed, then I multiply by 1,000. So a large value like meters cubed down into decimeter cubed multiplied by 1,000, that's 15 decimeter cubed. And to get into centimeters cubed, I multiply by 1,000 again to get into even smaller unit value, 15,000 centimeters cubed. So calculate the volume in centimeter cubed. I've done that. 15,000 centimeter cubed of butane gas. Now calculate the volume of 38.8 grams of liquid butane. It's got a density again. So density is mass divided by volume. Easy this time. Density is 0.6 grams per decimeter cubed. So the mass is in grams. 38.8 I want in grams. Yes, it's already in grams. And the volume is going to come out in centimeter cubed because density is grams per centimeter cubed. So the volume, rearrange that. Volume is 38.8 divided by 0.6, 64.67, and it comes out in centimeter cubed. And then finally use your answers to calculate a factor. That means sort of like a multiplication factor by which butane expands when it changes from a liquid to a gas. So the difference here is I've got this as a gas, I've got butane as a gas, I've got the same amount, the same number of, same mass of butane now as a liquid, and they occupy different volumes. To work out a ratio, which is another word for a factor, I divide one by the other. 15,000 by 64.67 is 232. So it expands, increases its volume by 232 times. I'll put it to 3 significant figures because most of my other values are to 3 significant figures, 232.